Hello everybody. As Connor said, my name is Mathias Hudoba de Badyn. I'm a third-year physics and mathematics student at University of British Columbia. And this summer I had the privilege of working with James Owen at the Canadian Institute for Theoretical Astrophysics. So my talk is titled Thermal Sweeping in Late Protoplanetary Disk Lifetimes. So basically a protoplanetary disk forms after the period of star formation. So from Astro 201 or equivalent, we know that stars form from a nebula. Due to gravitational instabilities, the gas and dust in the nebula collapse. This process is actually a form of accretion, where the gas basically falls into the center due to viscous processes, and it forms an accretion disk around the star. And so a protoplanetary disk is defined as the object left over after star formation. It's very dust heavy, and it's called protoplanetary because it's thought to form planets. So my work was basically in figuring out how these things die, in particular their late periods of their evolution. There's three ways that a protoplanetary disk can dissipate. The first is through accretion, where gas falls based on angular momentum transport processes. The gas will fall inside and onto the star, and the disk will basically dissipate through that mechanism. The second one, which I'll be talking about, is photoevaporation. Photoevaporation is basically, it's self-explanatory. Light from the star basically evaporates gas and dust away from the disk. And the third method is planet formation. When a planet forms, it creates a gap in the disk, which creates a lot of instabilities, and gas will be lost through the disk in that process as well, but that's a very lengthy subject, and I will not talk too much about that. So in photoevaporation, the first models only included ultraviolet light, and dubbed the ultraviolet switch by Clark et al. So how this process created one interesting result, in that there is a point in the disk where the mass loss rates, the amount of mass being lost through photoevaporation, will be greater than the amount of material falling inwards through accretion. And so a gap forms at this radius because it's not being replenished by accretion. And so what happens is you get two disks. This disk is very thin, and so it doesn't have a very large surface area to be photoevaporated away. It dies based on almost completely accretion processes. And that leaves a very large inner edge for this outer disk to be photoevaporated away. Unfortunately, the original models, including only ultraviolet light, did not give enough mass loss to account for the lifetimes of observed disks. So because young stars are extremely X-ray luminous in their early stages, the further models included X-ray photoevaporation. And that's different from ultraviolet light, ultraviolet photoevaporation, because X-rays work by ionizing the gas. They eject electrons, whereas ultraviolet light only increases the energy level of the electrons. And so it's a very different process. So my supervisor, in his work, came up with this interesting mechanism called thermal sweeping. So basically, if we look at this is half of a disk. So imagine the star is here. The disk looks like, the cross-section of the disk is here. It's symmetric over the x-plane, so I didn't draw this part of it. What happens here is, if you take delta to be the X-ray penetration depth, so up to here, X-rays will penetrate and heat the gas. Past here, this is only heated through thermal processes in the dust region of the disk. So what happens when the scale height, the vertical scale height of the disk, is much greater than the X-ray penetration depth? Thermal processes from heating will not be sufficient enough to create instabilities in the disk. So what happens is, when the X-rays heat this region, the disk will puff up a little bit, but because the dynamical time scale for the puffing is